negative experience with what I described as true.
We have samosas and bun cakes for everyone. We're going to help pass out. So just stay seated and they'll end up coming to you eventually. Without further ado, here's Sasha. If you have any questions, just raise your hand during the presentation and don't feel free to stop now.
All right. Great. Hi, everyone. How are we doing today? Good. I think you can do better than that. How are we doing? All right, that's exactly the kind of enthusiasm we need to talk about quantum computing. But before we talk about quantum computing, I wanted to talk about my grandmother. And she was recently diagnosed with dementia, which is kind of scary to me because I don't know if she'll remember who I am in the next 1 or 2 years. And currently, our drug discovery methods for diseases that are incurable, like Alzheimer's, include a lot of computer simulation. So kind of like modeling how these molecules will interact in the body. But currently, our computers are actually pretty bad at doing that. And so when I learned about quantum computing, which is kind of like a revolutionary form of computing that has amazing applications for drug discovery, I got really excited about quantum computing, and that's why I chose to study it and why I want to share it with you. Also, I don't know what I'm looking at in this photo. Maybe it was like goldfish. I don't know. I really liked goldfish as a kid, but yeah, I thought it was funny. So yeah, speaking more broadly, a lot of current and future global problems necessitate really fast computing. So one of these is travel efficiency. So as our global resources in the world kind of dwindle over time, we want to be as efficient as possible with how we travel. So that means we want to get to our destination as fast as possible with as little resources used as possible. And that requires kind of fast computing to figure out the best way to do that. We also have drug discovery, which I talked about. You need really fast computers to figure out how drugs will interact in the body because that's a very complex system and has a lot of parameters involved. We also have climate change. I know we all came from that climate assembly, and our senator talked kind of a bit about how there's different technologies being developed now for sucking CO2 out of the atmosphere, for example. So to model kind of to model different drugs that are able to do this, we need to kind of simulate these drugs and how they would actually interact in an environment, and that requires fast computing. And finally, we have machine learning. For those of you who have ran a machine learning model before, you might know the pain of waiting for your model to train. And that's because machine learning requires a lot of data, and to build better models, we're going to need even more data, and that means faster computing. And so for a more concrete example, I want you to consider the traveling salesman. Who has heard of the traveling salesman before? Okay, so a few of you, yeah. So imagine that you're a delivery driver, and you have 24 locations across the US to visit. My question to you is, what is the shortest possible path you can take to reach all of these destinations? And maybe more importantly, how would you go about solving this problem? So I'll give you a few seconds to think about this. All right. So if you had trouble with this problem, that's okay, because even our best supercomputers have a lot of difficulty with problems like this. So for a classical computer, 24 cities are visited, and that means there's 24 factorial possible ways you can reach all these cities. And that amounts to about 6 times 10 to the 23 ways. That's basically a number that we can't even think of. And in terms of computing time, that's about 3 times 10 to the 9 years. So this is basically, oh, sorry, I think I pressed a button. Okay. This is basically an intractable problem. So this is just an example of an optimization problem that falls in the scheme that even our best supercomputers have trouble with. So in general, even our fastest supercomputers have trouble solving specific kinds of problems, like optimization problems, with large amounts of data in a reasonable amount of time. And this is where quantum computers come in. And this is a photo of a quantum computer. So before we can understand quantum computing, we need to understand a bit of background on quantum mechanics. So quantum mechanics are fundamentally different from classical mechanics because they govern the really small in our universe. And things behave really weirdly. So I thought this analogy was kind of funny and kind of useful in understanding these three properties of quantum mechanics. So we have a Euro processor and different EU bits, which are countries. And our first property is superposition. So the analogy here is that Germany is in a superposition of states because Germany is kind of thinking about two different opposing ideologies. And this refers to the property in quantum mechanics where a quantum mechanical object can be in a superposition of states, so it can be in two different states at once. And next, we have entanglement. And the analogy here is that Sweden and Finland, their votes are both hinged on whether Denmark votes yes. And so this describes the quantum mechanical property where different quantum mechanical objects can be correlated. Their states can be correlated across infinite distance. And finally, we have interference. So here the analogy is that Germany and France have opposing beliefs, but when you kind of take them together, their view is kind of neutral. And this is kind of referring to the quantum mechanical property where like quantum mechanical objects can be waves, and when you combine their states in interesting ways, they can actually cancel out. And so now we can talk about quantum computing. Quantum mechanics allows for an entirely different form of computation because you're operating under different laws of physics. And so I want you to consider a bit, which is what our computers use to do basically everything they do. A bit is a piece of information, and it can either be 0 or 1 at any given time. And that's how our computers store and manipulate information through different logical gates. On the other hand, a qubit is what a quantum computer used to perform computation. And a qubit can be in a superposition of states at any given time. So remember when I talked about superposition on the previous slide? This qubit can basically be 0 and 1 at the same time. So that can be quite confusing, but it's actually a very important part of quantum mechanics that allows us to do pretty cool things. So quantum computing is all about exploiting quantum mechanics for computational speedups. I want to give a bit more context about quantum computing. So how many of you have heard of quantum computing before this presentation? Okay, well, that actually surprises me, but I think this is still going to be useful. So in 1981, that was the first time a quantum computer was proposed. And moving into the late 90s, there were actually quantum algorithms being developed. So this is the time when people realized that quantum computing could actually be really profound and a new way to compute. So an example of this is the integer factorization algorithm, which is Shor's algorithm. And that's kind of been a big deal recently because if this algorithm is actually implemented on a quantum computer, it could basically break RSA encryption, which relies on kind of the inability to factor really, really large prime numbers. And moving into the 2000s, a lot of companies started working on hardware. So how are we actually going to build these quantum computers? So companies like IBM and Google, and also a lot of research at universities, focused on these things. And finally, in 2019, this was a big deal when Google demonstrated quantum supremacy. So that basically means that Google showed that a quantum computer could do a problem that a classical computer couldn't solve. And so that really demonstrates that quantum computing is kind of a growing field, and it shows a lot of promise. So you may be wondering, if quantum computers can solve these like really hard problems, like why aren't we using them and why aren't they good enough? And that's because physical quantum states are fragile to everyday environmental perturbations. So I don't think you would notice a stray photon hitting your eye. But for a qubit, that could mean a difference between being in a 0 state and being in a 1 state. And so these noise factors also include shifting magnetic and electric fields, which can dramatically alter the state of any sort of qubit, and also radiation, including cosmic rays. And it's really difficult to isolate quantum systems from these types of noise. And that's why it's been really hard to build practical quantum hardware over the last decade. And this is where error correction comes in. So I'm going to be talking about this paper by Google Quantum AI. And this was a big deal because the researchers found that they could add more qubits to their system, and that would somehow provide a sort of protection to their algorithm versus increasing the error in their system. And they did this through an error correction method. And this is important because we want to scale quantum computers for practical use, but we can only do that if we have scalable, fault-tolerant qubits. And that means our individual qubits have to be protected enough from error. And so the aim of this study was to show that we can overcome the additional risk of adding qubits to our system by gaining a sort of protection through this error correction method. And I want to point out that this study was published only about 2 months ago, so this really represents the latest in this field. So to introduce some terminology, I want you to imagine that you're taking a test. And not like a Nueva take-home test, but a test where you're actually in person in a classroom and working by yourself. And now imagine that you can collaborate with your peers. So you can share your knowledge with them and kind of share answers. And wouldn't you think that when you share your answers with your peers, the class average on the test would be higher, right? Because you're all sharing your knowledge and the differences in that knowledge would kind of overlap and create a higher accuracy. So to introduce some terminology here, in the study, the researchers referred to physical qubits as like the individual students in the class and their associated individual knowledge. So these are actually the physical small pieces of information in the system. Whereas a logical qubit could be the class and its collective knowledge. And you can think of the logical qubit as kind of like an individual physical qubit, but it has many constituent parts. And so this terminology is going to be useful to describe what the researchers did. So here we have the setup for the study. This is a quantum processor, and each one of these little squares represents a qubit. And the yellow qubits here you can think of as the students in the class taking the test, whereas the blue qubits are the students that are used to infer the state of the yellow qubits. And this is because there's a quantum mechanical property where if you measure a quantum object, its state will actually collapse. And that's really problematic. And so these blue qubits are used to kind of guess the state of the yellow qubit without disturbing it. And here in this study, the researchers had a distance 5 and a distance 3 grid of qubits. So the distance 5 grid is this 5 by 5 grid of yellow squares. You can see 5 on the bottom and 5 going up. And the distance 3 refers to a 3 by 3 subset on this grid. So you can see subset distance 3 is outlined in red. So you have 3 qubits along the bottom here and 3 going up. And so the researchers set the study up this way to show that the distance 5 grid would have higher fidelity than the distance 3. And that would mean that the researchers were able to add physical qubits to their system, and they could improve on error over a system with less qubits, which is the distance 3. And I want to note that accomplishing less error with more physical qubits has never actually been done before. So this is where the novelty of the study really lies. Do we have any questions so far? Yeah, Mason.
What's the purpose of the unused qubits?
Yeah, so the unused qubits are just qubits that are on the processor, because this processor was actually built not specifically for the study. There have been a lot of different experiments on it, but they're just qubits that, well, this whole thing is the processor, but these qubits are unused because they're only kind of using these qubits for their specific experiment. And so, I mean, if they specifically built a processor, they would only need the qubits they're using, but they're using one that was already built, so it has these other qubits. Does that make sense? Yeah, Jenna.
I think this is off topic, but what is it all data?
Yeah, so, yeah. So it actually, I'll go back a little bit. It looks like this in real life. But this is basically a superconducting quantum processor. I don't know a lot about like the material science and how this was made, but all I know really is that the qubits could be encoded in some sort of physical setup, and that's what this processor is. Yeah. Yeah, it's here.
How do you measure qubits or like see properties?
Yeah. So it's all about kind of like sending in signals and sending them out. So in practice, it's kind of like CS. You don't really know like what is actually happening on the hardware, but you know kind of like your input. And so you can do the same thing kind of for quantum computers. So you can write code to kind of send inputs and kind of receive the states of the qubits through different like signals. I don't know much about that either, but yeah. Andy.
So you said that you're trying to measure a qubit directly, its state will collapse, right?
Yes.
So if you're measuring it by like its proxy qubits, or like the ones around it, how do you measure those ones without them collapsing?
Well, they do collapse, but the thing is we only really care about these yellow qubits. The blue qubits are solely used to infer kind of the states of the yellow qubits. So it's okay if they collapse, yeah. Yeah. Okay. Yeah, Elise.
Could you talk about the error correction methods you mentioned earlier?
Yeah, well, okay, so that's a little bit beyond the scope of this presentation, but I'd love to talk with you after it. Yeah. So I wanted to get into results now. So the researchers ran error correction cycles over time, and that's what this x-axis here represents. There's actually two graphs here, so don't get confused, but they have the same x-axis. And so over time, they ran this error correction cycle. And on the y-axis here, in graph A, we have logical error probability. And that basically means the error that the probability that an error occurred. And there's actually kind of a complex way they did this, but that's also beyond the scope of this presentation, but I can talk with you after if you're interested in that. And so the meaningful thing here, looking at the legend, the red triangles represent the distance 3 average. So the average error for the distance 3 grid, which is the 3 by 3 grid of qubits. And the blue pentagon is the 5 by 5 grid. So what was the average error for the 5 by 5 grid of qubits? And the important thing here is that you can see that for every single error correction cycle, the average for the 5 by 5 grid was below the average for the 3 by 3 grid. And that's what they were looking to show. So through their error correction method, the researchers could actually improve on error and show that they could add more physical qubits to their system, and that could basically provide protection. And this figure B here is kind of like the same sort of graph, but instead of plotting logical error probability, you're plotting logical fidelity. And it's plotted on a log scale, and that means that we can basically turn this curve into a straight line, and that's useful because we can extract a slope from that, and that's what they did here. So they found the error rates for the distance 3 and the distance 5. And you can see that there's a pretty small difference, but again, this is meaningful because it's never been done before. It's never been shown that you can add more qubits to a system and decrease the error in that system. Yeah?
Is 5 qubits like a lot of qubits, or like how many qubits does like the full quantum computer have?
Yeah, so I'm pretty sure that the entire processor had 53 qubits. And 5 qubits is not a lot. It's not really a meaningful amount to do practical applications. I think it was estimated that we need like thousands of qubits to do like real like practical applications. But this processor was kind of like an earlier processor that was made, and it's mainly just been used to do experiments and not really for practical like applications. Does that make sense? Yeah. Okay. So going back to results. Yeah, so there's a small but relevant difference in the logical fidelity between the two surface code sizes. And so moving on to more results here, I want to talk about this graph. And I'll go through axes a bit because it's a little bit confusing. So epsilon 3 here is just from the previous slide. So it's basically the percent error for the distance 3 grid, so the 3 by 3 grid. And epsilon 5 on the y-axis is the error for the distance 5 grid. And so for this graph, you're essentially just plotting the fidelity of the 3 by 3 grid against the fidelity of the 5 by 5 grid. So each of these points represents one trial of the experiment. And so for each trial, the researchers are saying, what was the fidelity of the 3 by 3 grid, and what was the fidelity of the 5 by 5 grid? And then they plot that point. So if you think about this, this vertical line here means that the error in the 3 by 3 grid was the same as the error in the 5 by 5 grid. And so for anything under this line, that means that the 3 by 3 grid performed better than the 5 by 5 grid, because you have a greater fidelity in the 3 by 3 grid than the 5 by 5. And so you can see that as researchers kind of improve their setup through these 3 ways, they were able to kind of move up on this graph, which corresponds to the 5 by 5 grid performing better. And you can see that it performed better, almost twice as much better. This is about a slope of 2, until it actually overtook the 3 by 3 grid here at the top. And that's basically what this graph is kind of showing. This graph here is just the last point on this graph. And so this is really important because the researchers were able to show that adding more qubits kind of like improve their system, and it improves twice as fast as a smaller system. And that's really important. So kind of takeaways and outlook of this paper. This paper represents a really key step in error correction, which is what researchers have decided is the next step in building a scalable quantum computer, because we've kind of decided that we can't completely isolate quantum systems from noise. And so we need ways to combat this noise instead of trying to prevent it. And also, more experimentation is necessary. So this study only looked at a 5 by 5 grid versus a 3 by 3 grid of qubits. But what if you tried something like a 25 by 25 grid of qubits versus a 30 by 30 grid? How would that perform? We don't know. And that's why more experimentation is necessary. And also, the study said that component performance must improve by at least 20% to move below threshold, and substantially improve beyond that to achieve practical scaling. So this means that component performance, which is just like performance of the individual qubits, that needs to improve by at least 20% to move beyond this threshold. And this threshold is where you can add more qubits to a system, and that'll provide protection versus more error. And so this just really highlights that this is a good step in the process in building a scalable practical quantum computer. But we really need more work in this field to get to that point. And so tying it all together, with a scalable quantum computer, we'll be able to accelerate drug discovery, which is what I started this presentation with. But beyond that, we'll be able to simulate other kinds of molecules. These are just some news articles that I read recently. There's actually a quantum computer specifically installed for healthcare research. Ford enlisted quantum computing in EV battery materials hunt. That's a big deal because that kind of shows where quantum computer can like aid materials design. We have Playing Up the Atmosphere for Quantum Computing. This was a paper that showed that we can kind of use quantum computing to simulate molecules to take CO2 out of the atmosphere. And in general, I just find it incredible that we can exploit these fundamental properties of the universe, to solve issues that we really care about. So I think it's just really cool that we can take what we have, that's kind of just a fact of nature, and do something really cool with it that can help a lot of people. So here's some comments and acknowledgements. I want to thank Ted, because I could not have understood this paper without him. Also, join Datas if you're interested. Just email me and come to Quantum Club. Also, if this was interesting for you, we'll actually host a guest speaker from Google Quantum AI next week, and he'll talk about quantum computing for climate solutions. So with all of that, I want to thank you for your time.